Morning students, in this video we are going to learn about interference in PH3151 Engineering Physics from Unit 3. I am G. Indra, Assistant Professor from Department of Physics, GCE, Singipatti, Tanjavur. In this video we are going to discuss about the topics interference, theory of air wedge, experiment to determine the thickness of the given wire by forming air wedge, Michelson interferometer and applications of Michelson interferometer. First topic is interference. What is interference? So generally for light, interference will occur for light uh, when two light waves from different coherent sources that meet together, then the distribution of light due to one wave is disturbed by the other. The as a result, the modification in the distribution of light will be uh, produced. The modification or change of the intensity of light as a result of the superposition of two or more two or more waves of light is generally called the phenomenon interference. Uh, the important thing is for the process of for the phenomenon of interference, we need two monochromatic sources. So generally, a light that is emerging out from a single source using a double slit separated by a distance is used. So the light that passing these two slits will act as a two individual sources. So these two individual sources, the light emerging out from these two slits, that will interfere with each other. So as a result, the interference fringes, the interference patterns will be appearing in the screen. So interference is the phenomenon in which the modification or change of intensity of light resulting from the superposition of two or more waves of light, so which is called interference. Next topic is theory of air wedge experiment. First, let us see what is air wedge. Air wedge means a wedge-shaped air film is formed between two glass plates. These two glass plate is placing one over another by keeping the wire in one end and the other end is made to contact with each other. So in between a thin layer of uh, air gap is produced. So the shape of the air gap will be in the wedge shape. So that's why we call it as a air wedge. Uh, Actually, the phenomenon interference is occurred that will explain the basis of the wave theory of light. So here the light coming from the source that is made to fall on the top glass, that is glass plate. So that is penetrating to the glass and that is entering to this air wedge. So here the air wedge, the top surface of the air wedge, which means the bottom surface of the glass plate. So the light is being reflected from that surface. As well, the top surface of the glass plate, that the bottom surface of the air wedge. From that also the light is getting reflected. So these two reflected light that will interfere each other. So as a result, we will observe the interference pattern. So generally the air wedge is formed between the two glass plates by introducing a wire or a piece of paper within the glass plate. So a air wedge is formed. So this is known as air wedge. When you observe the interference pattern from the air wedge, you will see the alternate dark and light fringes like this. So the thickness of the air film increases towards from the line of contact O to the point where the wire is placed. The light ray from a monochromatic source is made to incident perpendicular on the air film. So the incident ray of light is partially reflected from the top surface of the air wedge as well as partially reflected from the bottom surface of the air wedge. So these two reflected rays that will interfere, as a result, interference fringes will be produced. So these two reflected ray will interfere and large number of straight alternative bright and the dark fringes are formed. That is shown here. This is the interference pattern produced by the air wedge experiment. So we can observe the alternate dark and bright fringes. So in this air wedge experimental setup, we will see this one. From the previous slide, we can locate the nth dark band that is located at the distance of x meter from the point of contact of the glass plate O. The wedge angle is the small angle formed between these two glass plate, that is theta, that is represented as the theta. Then the path difference between the two reflected rays is represented using this expression 2 mu t cos r is equal to n lambda. Here mu is the refractive index of the air medium. So we are considering air medium. So the value of mu will be equal to 1. T is the thickness of the wire used. R is the angle of refraction. So the angle of refraction will be approximately equal to 0. So the value of cos 0 that is equal to 1. So therefore the path difference equation will be modified into 2t is equal to n lambda. Lambda is the wavelength of the monochromatic light source used. X, since x is the distance of the nth band from the edge of contact O, t by x that is equal to tan theta. If theta is very small, tan theta is approximately equal to theta. So we can write t by x is equal to theta. That means the angle of the air wedge. Similarly, for the next dark band, which means nth band is one dark band, next dark band is n plus 1th dark band. So similarly for n plus 1th dark band, we can write 2 into t plus beta into theta equal to n plus 1 into lambda. So the 2t is equal to n lambda. Here we are writing. Similarly, when you move from n to n plus 1th band, so bandwidth is the distance between the complete length of one dark and one light fringes will be the bandwidth that we will write as a beta. So when you move from nth dark band to n plus 1th dark band, you are just moving to one complete bandwidth. So that's why we are writing 2t plus beta into theta, that is equal to n plus 1 into lambda. So by taking the difference of these two equations, we can write 2 beta theta is equal to lambda. So which implies beta is equal to lambda by 2 theta. So this is the expression for the bandwidth produced by forming air wedge. So in the air wedge experiment, the expression for bandwidth is equal to beta is equal to lambda by 2 theta. Lambda is the wavelength of the monochromatic source. Theta is the air wedge angle. Using the expression of the fringe width, which means the bandwidth beta, we can determine the thickness of the thin wire that is introduced between the two glass plate to form air wedge. So the expression to determine the thickness of a thin wire or a very thin foil that is introduced between two glass plate to form the air wedge. is discussed here. The given wire whose thickness D is to be measured is placed in between two glass plates. A air wedge is formed between these two glass plates. If L is its distance from the edge of contact to the wire introduced. So in the previous slide, I have shown that L is the length of the air wedge and D is the thickness of the wire that introduced between the two glass plates. So here is the expression for tan theta. Here the theta is the angle of the air wedge. Tan theta is equal to D by L. Here the angle of air wedge will be very small, that is nearly zero. So for a small theta, the tan theta will be equal to theta. So theta is equal to D by L. So which implies the expression for the fringe width beta is equal to lambda L by 2D. So when you measure the fringe width using the vernier microscope, the monochromatic source which we are used, whose wavelength is lambda. So that is known thing. So when you measure the length of the air wedge, we will determine the thickness of the wire D. So rearranging the expression for beta, we get the thickness of the wire or a sheet introduced between the glass plates. By using this expression, D is equal to lambda L by 2 beta. So the thickness of the thin foil or thin paper sheet or a small wire or a human hair will be determined by forming a air wedge using that between two glass plates. By measuring the bandwidth beta, we will determine the thickness of the material, thickness of the thing. Next, applications of air wedge. Determination of diameter of a wire or thickness of a thin sheet of paper which is introduced between the two plain glass plates that is in contact with the one edge. On the other edge side, the small wire is introduced. So a thin wedge shaped air film is formed in between these two glass plates. That is the air wedge is found between these two glass plates. Theta is the very small angle, that is the angle of air wedge. So this figure illustrates the experimental setup of the air wedge experiment to determine the thickness of the wire. So in this figure, a small wire is placed between two glass plates. So one end of the glass plate is made to contact and other end a wire is introduced near to this side. So the monochromatic sodium vapor lamp is act as a source. So light from the source is made to incidence on the glass plate G, that is kept for 45-degree inclined to the light source. So the light is reflected from this glass plate and that is made to fall on this air wedge. So this light will penetrate through the top glass and the light is getting reflected from the top surface of the air wedge and as well as the bottom surface of the air wedge. These two reflected light will interfere each other. So as a result, the interference patterns will be observed in the microscope. Um, we can see the alternate dark and bright fringes. While viewing through the microscope, we will observe the interference pattern. The interference pattern consisting of a bright and dark bands of equal width when we view through the traveling microscope arrangement that shown in the previous slide. The microscope is focused and the clear image of the interference fringes will be observed. Uh, then the crosswire in the microscope is coincide with the one dark band, so that we can take it as a nth band. Um, the reading is noted. So in the reading from the horizontal scale of the drawing vernier microscope, at the nth band position, the reading is noted from the drawing vernier microscope horizontal scale. Then the using the screw, the using the screw setup, it is suggested that the cross wire from the nth band is moved to the n plus fifth band. So now the reading is noted. So the reading is noted for nth band, n plus fifth band. So likewise n plus 10th band, 15th band. So accordingly, the reading taken for nth band, n plus fifth band, and n plus 10th band, etc. is recorded. That is entered in the tabular column. From the tabular column, the average fringe width beta is determined. So by taking the difference of the reading for n plus 10th band to nth band, n plus 15th band to n plus 5th band. So every 10 band, we will get the fringe width 10 beta. So by dividing that 10 beta by 10, we will get the width of a 1 beta. So single fringe width beta we can determine. Also using this microscope, vernier microscope, the distance L between the edge of contact to the point where the wire is introduced is measured, that is L. Also by knowing the wavelength of the monochromatic light source lambda, we can determine the thickness of the wire using this formula. D is equal to lambda L by 2 beta meters. So beta is the fringe width that we are obtained from the tabular column. The reading is taken for nth band, n plus fifth band, then n plus 10th band. So every time the crosswire is moved for 5 bands. So the reading is from the microscope is reading in the horizontal scale of the microscope is noted. So difference between the n plus 10th band to the nth band will give the fringe width of 10 beta. By dividing this, we will get the fringe width of one band. That means the beta. So from the tabular column, we will get the average band width beta value. So using the beta value, we will determine the diameter of the wire that is introduced between the two glass plates to form the air wedge. Next, interferometer. An interferometer is an instrument which is used for measuring small changes in length, in wavelength. It is based on the principle of interference. So which works based on the principle of interference. The study of interferometer is called the branch interferometry. Michelson is the scientist who is originally designed the interferometer, which is used to find the wavelength of the monochromatic light source and the thickness of a thin strips. So this diagram shows the image of the Michelson's interferometer. Next, Michelson's interferometer principle. By dividing the light from a source into two parts, through partial reflection and refraction, two interfering beams are created. So from a single source, two interfering beams is created in Michelson interferometer. After being reflected by plane mirrors, these two perpendicular beams are ultimately brought together to create a interference fringes. So instead of a double source, here a single source is used and the light is by partial reflection and refraction, the light is splitted. So these two splitted light is reflected by the mirrors, and these two reflected rays is creating a path difference. As a result, the interference fringes is observed. in Michelson interferometer. Next, construction. Michelson interferometer is shown in figure. So here the light from the source S is collimated using the lens, collimating lens L. The parallel beam of light is made to incident on the glass plate G1. So G1 is a semi-silvered glass plate. So the light is incident on the glass plate. A part is getting reflected and a part is refracted. So the mirrors M1 and M2 is placed perpendicular to each other. The mirror M1 is placed inside a chamber C. So the reflected light from the glass plate G1 is meet the mirror M1 and the refracted light that is made to incident on the plain glass plate G2. So then that is refracted through the glass plate G2 and it is meets the mirror M2. So after that the reflected light from the M2 is reaching the G1 glass plate, semi-silver glass plate. So the mirror reflected light from the mirror M1 and the mirror M2 that will be captured through the telescope. So while viewing through the telescope, we will see the image of virtual image of the mirror M2 on mirror M1. So by moving the distance between the glass plate G1 and the mirror M2, we can adjust the path difference. Here the glass plate G2 is introduced to compensate the phase change. Since in G1 glass plate the reflected light that is penetrated through the glass plate G1 and reflected, so that is 2 times travel the distance of G1 glass plate. So that is entering and that is being reflected from the bottom surface of the G1 polished surface. So 2 times the travel through the glass plate and but the refracted ray that will pass only 1 time through the glass plate G1. So that length will be compensated by sending these to the glass plate G2. So the reflected light, these two reflected light will be in the same phase. The distance between the G1 glass plate and the mirror M2 will be adjusted, so the path difference will be created. So as a result, the interference pattern will be captured in the viewed through the telescope. Next, working of Michelson interferometer. From the previous slide, I showed that the light from the source S that is rendered parallel by using a collimating lens L. This light is made to fall on a semi-silvered glass plate G1. So the light beam is divided into 2 parts by this G1 glass plate. So one part of light is reflected to travel towards the mirror M1 that is placed in the chamber C. That we will call it as a ray 1, while the other part of the light is transmitted towards M2. So that is travel through the glass plate G2. So that I shown in the previous slide. So these light ray falls normally on mirror M1 and M2 and are reflected back along its original path. Yeah, so these light rays falls normally on M1 and M2. A path difference can be introduced between the two reflected rays by moving a mirror M1. So with respect to the glass G1, when we move the mirror M1, a path difference is introduced. So if we look through the telescope in the direction of mirror M1, we can see mirror M1 directly together with a virtual image of M2 denoted by M2 prime. So the reflected ray from M2 that reaches the semi-silvered glass plate G1 that is that is made to incident on the M1. So the light from the M2 again that meets the M1. So As a result, when we see the when we view the M1 through the telescope, we will see the M1 along with the virtual image of the M2 glass, M2 mirror, that is M2 prime. Hence, the ray reaching the telescope that appears to travel from M1 and M2 prime. So uh, it appears to be the ray is traveling between M1 and M2 prime. Thus, the Michelson interferometer system is optically similar to that of the interference from an air film enclosed between these two, that is M1 and the virtual image M2 prime. The interference fringes may be straight, circular or parabolic, etc. that depending upon the path difference and the angle between the M1 and the virtual image M2 prime. An air film is enclosed between two mirrors M1 and M2 prime. The two interfering beams appear from two virtual images S1 and S2 of the light source from S as shown in figure. So the light from the light source S, that is from the mirror M1 and the virtual image M2. So that is two sources S1 and S2. Let S1 and S2 be two virtual sources. The distance between the virtual sources is 2D. So the distance between the virtual sources M1 and M2 prime is 2D. So a ray 2, that is the ray is reflected from the mirror M2 that suffers reflection at the silvered surface of glass plate G1 again. So an additional path difference of lambda by 2 is introduced between the two rays. If we observe in the direction making an angle theta with the normal to the mirrors, the total path difference is written by 2d cos theta plus lambda by 2. For getting the maximum intensity in the interference process, 2d cos theta plus lambda by 2 is equal to n. Lambda is the condition where n is equal to 0, 1, 2, etc. So this is the condition for maximum intensity. 2d cos theta plus lambda by 2 is equal to n lambda. So these are all the types of fringes that is uh, uh, obtained in the Michelson interferometer experiment. So these are all the possible types of fringes. When the two images M1 and M2, so M1 is the mirror, M2 prime is the virtual image of the mirror M2 on M1. If these two is coincides, there is no path difference. So the light will be there is no interference patterns. The uniform distribution of light is appeared here in A. In B, the distance, so the mirror M1 and the mirror M2 prime, the virtual image is separated. A small air film is introduced between these two. So as a result, a circular fringes is produced, that is shown in figure B. In figure C, the virtual image is like this, a wedge shaped thing is formed. So we will get a parallel alternate dark and bright fringes like this. In the figure D, the M1 and M2 will be if like this. M2 virtual image is over M1 and in this orientation we will see this type of fringes. So in D and E, the M1 and M2 will be in the orientation in this figure. So these are all the different type of fringes observed in the Michelson interferometer. Applications of Michelson's interferometer. The Michelson interferometer is used to find the wavelength of a given light source. The refractive index and thickness of a transparent material will be determined using the Michelson's interferometer. The Michelson interferometer is used to find the resolution of wavelengths as well as the standardization of meter. Wavelength determination using the Michelson's interferometer. So the setup of the Michelson interferometer I have explained in the previous slide. So using a monochromatic light of unknown wavelength, the Michelson's interferometer is adjusted for a circular fringes. So the position of mirror M1 is adjusted till a particular bright fringe coincide with the cross wire. Now the micrometer screw reading is noted. So at this point the reading is noted. When the mirror M1 is slowly moved, so the number of fringes that is N, we denote it as N, that moved across the field of view of the telescope is counted. So this may be of the order of 20, 30 fringes, etc. So again the micrometer screw reading is noted. So the distance D moved by the mirror M1 is given by the difference between the initial and final micrometer screw readings. When the mirror M1 is moved through the distance lambda by 2, the path difference changes by lambda by 2. The position of a particular bright fringe across the crosswire is replaced by the next bright fringe. So for one fringe shift, the distance moved by the mirror M1 is equal to lambda. Let M1 move through the distance D, and the number of fringes that moving across the field of view will be counted, that is taken as N. For the shift of N fringes, the distance moved by the mirror M2 is D. So D is equal to N lambda by 2, which implies wavelength lambda is equal to 2D by N. So by using the distance moved by the micrometer, that is D, and the number of fringes moves across the field of view for moving the distance D, so using these two, the wavelength of the source lambda will be calculated by using the formula lambda is equal to 2D by N. Next, determination of thickness of a thin transparent sheet using the Michelson interferometer. The experimental setup is shown in this figure. So the same procedure up to previous thing, the last I have told no. So we are counting the number of fringes N for the particular distance moved. In that position, a thin sheet is introduced between these two glass plate, between Z2 glass plate and the mirror M2. So as a result, a path difference is introduced between the light. So the path difference is 2 times the thickness into mu minus 1. So mu is the refractive index of the thin sheet used. So the thickness is calculated. So by introducing the thin sheet, the number of fringes crossed the field of view will be counted. That is taken as N. So using that N, the thickness of the thin sheet small t will be calculated using this formula. T is equal to N lambda divided by 2 into mu minus 1. Thank you.